Welcome back to Sigma Maths. This is the 6th video in the Exponentials and Logs series, and we will be practicing the logs and nonlinear data. Let's start with question 1. In this question we have been given some data for x and y, and we've been told that the data follows a trend of the form y equals ab to the x. This form is called the exponential form. We're then told that a graph of log y against x is plotted and a line of best fit is drawn. We've got some information about that line of best fit. We've got a point that it goes through and the gradient. Part A, write down the equation of the line of best fit. So if you think purely about coordinate geometry here, we have enough information as we have a point and we have a gradient. So we could jump into something like y minus y1 equals mx minus x1. However, be cautious, because that might lead you to just have a y in your equation when actually what you need is a log y. So I'm going to go with the plus c method. So I'm going to write down my equation of the line so far as log y equals my gradient 0.36x, because being an exponential function, remember when we log exponential functions we do not log the x as well, as it turns out. And then I'm going to just leave my unknown as c. So now I can put these values in, bearing in mind that this is my x coordinate and this is actually my log y coordinate. So I will put in 3.0 for log y, 0.36 multiplied by 5.5 for x, and this therefore I can find out my c. Okay, and that gets me 1.02. So my final answer to part A then is log y equals 0.36x plus a 1.02. Okay, part B, work out the values of the constants a and b to two significant figures. This is where we go back to the original model, we apply logs to both sides and we compare that to our straight line equation that we worked out in part A. So we start with y equals ab to the x, and then remember we need to show the examiner that we know how to go from the exponential equation here to the linear log equation. Oh, missing a y there. So I'm going to make sure I write at least one line of working down. So remember here we split apart using addition, so log a plus x comes down because it is a power, x log b. Okay, so here I can directly compare with part A. So my 0.36 must line up with my log b because it is the coefficient of x. So log b equals 0.36. Remember here, if we see a log without any base written with it, then we know it's base 10. So b is 10 to the 0.36, which is 2.29, which if I remember the question saying two significant figures, so that should be 2.3. And then log a, well this is the y-intercept or the constant term, this must be equal to the 1.02. So a again, base 10, so 10 to the 1.02, and we get 10.47, etc. So again, two significant figures, that's just going to be 10. Okay, part C, use your answer to part B to predict the value of y when x is 5. So first of all, I'll write out the model with the values that I found so far. So a times b to the x, a times b to the power of x. Okay, remembering not to be tempted to do 10 times 2.3 here. Now I can simply put my power of 5 in there, x equals 5, and pop that into my calculator. And we get 636 And 43.6, remember the question here has asked for 1 decimal place. There are no units to give because this question did not have a context. So we are done. Okay, question 2. So here we have people volunteering for a charity, so that's represented by V, after T years from 2011. And we have, right, that one is a polynomial equation because our independent variable there is the base number rather than the power. We've got over a period of 10 years. Okay, we've got a graph of log V against log T. So again, that also lines in with it being a polynomial model. And we also have a line of best fit shown on the graph, and we've got some information here. Use the information in the graph to work out the values of P and Q. Right, so this isn't as structured as previous questions. So we know that we're going to have to look at the equation of this straight line, and we're going to have to look at logging the original equation and linking up the values that we've got. Let's start by writing down the equation of the straight line. We already know the intercept here, 0.21. However, we only know one other point that it goes through. We don't actually know the gradient yet, so we're going to have to calculate the gradient. I'm going to do that in this working space here. So our gradient, I'm going to use m to represent my gradient. It's going to be 0.84 minus 0.21, the difference in y, over difference in x. Let's see what that comes out as. So we get a gradient of 2.1. That means we can now write down our equation of the line of best fit. So that will be log v, remembering to be careful to use these here for your y and x. So log v equals 2.1 log t plus 0.21. Okay. Now we're going to need to compare that back to our original model using logs so that we can get something in P and Q. So let's take our V equals P T to the Q and log both sides. Log V equals log of P T to the Q. And then we'll split it apart. So again, addition to split the multiplication, and the power comes down. Log t, there we go. Right, direct comparison again. So let's see, 0.21 here is the constant term, log p is the constant term. So log p therefore must equal 0.21, and then the coefficient of log t is q, and the coefficient of log t here is 2.1. Well, there you go, that's quite easy. Q is just 2.1, nothing to do there, but over here we are going to need to raise both sides to the power of 10 to get 1.6, and I'll stop there. It's 1.62, but I'll just check in the question, 2 significant figures, so 1.6 is enough. Use the model to predict the number of volunteers in the charity 15 years after 2011. So I'll write my model down. V equals P 1.6 times T to the 2.1. Now we can put our number in. So it's 15 years. So this was T years from 2011. So I just need to put 15 to the 2.1. Pop that into our calculator. Okay, so it looks like after 15 years the company had, the charity had 472. It's 471.96. We round that up for 472 volunteers. It says comment on the accuracy of your answer. Okay, so this is actually a little bit of stats that we have to think about here, because we were told that the data was recorded over a period of 10 years from 2011, and here we've put in 15 years. So this is not in the range of data, so not accurate. As 15 is not in the range of data. And there's a posh word for this, which I'm also going to include in my answer. Extrapolation. Okay, so interpolation is when you're within your range of data, extrapolation when you're not. And when you work things out by extrapolating, they tend not to be accurate answers. Okay, so that is question 2 done. Let's have a look at question 3. Okay, so data is coded using capital Y equals log Y, capital X equals X to give a linear relationship. The equation of the line of best fit of the coded data, so coded just means it's been transformed as said in the question, capital Y equals 0.9 plus 6.1 capital X. State whether the relationship between X and Y is exponential or polynomial and write down an equation for this relationship, finding any constants that can be found. Okay, so this question actually requires us to know which way round it goes with exponential and polynomial. Remember, both of them have the log of the dependent variable, but one of them has log of independent and the other one just has the independent, stays as it is, and that's what we've got here. So either we remember this, or you could come up with a model for both and then just test each one by applying logs. Okay, so what we've got here then, seeing as our independent variable has not had log applied to it, is an exponential model. And we need to come up with a general equation for this so that we can have some constants to work out. So the original data is x and y, so I'm going to suggest that we use y equals ab to the power of x. We're going to compare this to the straight line graph that we have once we have applied logs to both sides. So let's do that now. You should be getting very used to this process by now. It's the same in every question. The only thing that changes is whether your independent variable is outside of a log or inside of a log. Okay, so I'm going to rewrite this straight line equation underneath this, but I'm going to replace the capital Y with log y. So 0.9 plus 6.1, and then the capital X can just be replaced with x, as in the question. And now we can pick out our values. So log A is 0.9, and log B is 6.1. Still working in base 10, so 10 to the 0.9 for A. Let's see what we get. Okay, so that gets us 7.9. I'll leave that to two significant figures. And then B is 10 to the 6.1. So let's see what that comes out as. Okay, so a very large number. 1, 2, 5, 8, 9, 2, 5. I'm not going to bother with decimal places there. Not going to make much difference to the number. So therefore we can write down a final answer. Y equals 7.9 times 1, 2, 5, 8, 9, 2, 5. There's about 1.3 million to the power of x. And we are done. Okay, final question. Question 4. So this time we've got price of shares in a company after a damaging media article was released. P equals AB to the T. So we've got another exponential model. Some values were recorded and used to plot a scatter graph of log P against T. This is all very familiar now. We're used to this. We've been given a line of best fit. Okay, so Nick drew a sketch of this line and worked out the x-intercept as shown below. Okay. Should really be t-intercept, but yeah, we see what he means. He says that because the x-intercept or t-intercept is 3.17, that means after 3.17 days, the value of the stock will be £0. Explain why Nick is wrong. Okay, well, he's certainly right about this 3.17 days because t is measured in days, so that's fine. But he's saying the value of the stock will be 0. So he's looking here and saying, okay, well, at that point there, you get 0 on the y-axis. And he's just automatically thinking, well, y-axis therefore represents the price, P. We know it does not. It is log P, in fact. So we need to state that, let's write it up here. Okay, Nick believes that as log p equals 0, when t equals 3.17, that means p equals 0. However, if log p equals 0, this actually implies that p equals 10 to the 0, which is 1. And there we go. So we've shown that it's not true, and we've given the correct answer. Part B, work out the values of a and b in the model, p equals ab to the t, give your answers to one decimal place. So yet again, we're going to do this same process. We are going to need, we've got this equation here already for us. So let's just apply logs to our model. Log p equals log ab to the t. And then we'll just write out the line separating it all out. Log a plus t log b. Comparing, we've got 0. Oh no, I'll do my logs first. Hold on. There we go. So log a equals 0.4914. So a is 10 to the 0.4914, which is, that would be 3.100, well, okay, just 3.1 then, because it's one decimal place. And then we also have that log b is the minus 0.1549. So b is 10 to the minus 0.1549. And that gives us a value of b being 0.7. Okay, so our final model then is that p equals 3.1 times 0.7 to the power of t. And you can see this kind of makes sense because it's an exponential model where the base is less than 1 will be one that's flipped around the y-axis. So if we would just have a quick look at that, so t against p, then it will be coming down like this, tending to 0, because it's an exponential model flipped around. It's just like having a negative in front of the t. And that seems to line up with the idea of the shares of a company falling in value over time. Okay, that brings us to the end of the video on logs and nonlinear data practice. I hope you found the video helpful, and if you did, please don't forget to hit the thumbs up button and subscribe if you'd like to see more. I'm looking forward to see you in the next one. Bye.